Don't worry, 10 hectares back in one. Everything better Actually, this is indeed amazing how effective they are. So what we can say now for sure? That all processes on micro level. Do you hear now better? All processes on micro level are indeed described by some variational principles. Actually physicists even don't think about any other option. If they need to describe any process on micro level, they just write Lagrangians, etc. However, if we go to, and so what does it say? That on micro level, there are very special reciprocities. Now perhaps I have to write what. You know, that's such small chalk remind. Yes. Okay. So we work hard. Yeah. All right. Okay. When we describe a mechanical system, as Francesca explained in the morning quite carefully, we have to start from kinematics. And when we start with kinematics, we say that our system is characterized by some set of numbers. The configuration of the system is described by some set of numbers. And now, where is physics? It turns out that to describe the physics, you have to prescribe just only one function. Only one function which depends on this, so this is the set of all these numbers which describe kinematics. We have to prescribe just one function. And this function completely determines the dynamical equations of your system. Namely, the dynamical equations look extremely simple. The dynamical equations of any mechanical system have the following form. You have to take derivative of this function with respect to coordinates and deduct time derivative of this function with respect to velocities. And that's it. So you see that the entire dynamics of the system is controlled by just one function. Here you have, say, you have n equations. This system has n equations, but if you would like, say, suppose you model some system and you wish to write n equations, you see how many entries any system of n equations has. A lot. But instead, the system has a very simple structure, like it is written here. You have to prescribe only one function, and that means that there are some very special reciprocities in the system. Let me give you a simple physical example. Say, suppose you consider motion of say you have a vessel filled with fluid, and you have a ball here, and this ball is moving is moving toward the bottom of this vessel. In this motion, you can describe the position of this ball just by one number q, right? And therefore, if you wish to write the equations of motion of this ball, and then you have to say how this function L, Lagrange, which is called Lagrange function, how this function depends on Q and Q dot. And Lagrange function of this ball is just kinetic energy. So if you compute kinetic energy of this system, and this ball is surrounded by a fluid, therefore when the ball is moving, then fluid is moving, fluid has some kinetic energy, you can compute this kinetic energy, and what you get as a result is the following function. You get kinetic energy will be certainly proportional to squared velocity of this ball, but there is a coefficient here which depends on the distance from of this ball from the bottom. And therefore, when you write this equation, let us write this equation for this specific function. What do we get? We have to take derivative of this function with respect to q. We get 1/2 dm dq times q dot squared minus ddt of derivative of this function with respect to q dot. And this would be what it is, mq dot squared, mq dot. And this is equal to 0, right? Or if I wish to simplify, then what would I get? If I differentiate the storm, I would get mq double dot. And when I differentiate this one, I get derivative of m with respect to q times q dot. So I get 1/2 m, 1/2 dm dq times q dot squared. So what we see that there is always, so to say, force acting on this ball, which is proportional to squared velocity. And this doesn't, so if you start from the force approach, say if you try to write that mass times acceleration equal to the force, it would be it is not an easy task to get such a term. When you start from energy approach, this is elementary. But what is more essential, that if you find the mass here, by the way, Poincaré defined what is mass. We are talking about masses of bodies, what they are. I guess the first person who really got some understanding of that was Poincaré, who said that mass is the coefficient near squared velocity in the expression for kinetic energy. And what we see here, that we cannot write correct equation if this mass depends on position. We cannot write correct equation without including this term. This I mean by variational reciprocities, I mean this fact that as soon as we know this function, some very intricate interrelations between equations appear. And where do they come from? We do not know. But what we know about nature, and perhaps this is the most basic law discovered by now about nature, that on microscopical level, all physical relationships possess this property. So all physical relationships, but at the moment we do not know any exception. Everything is so on micro level, everything is described by equation written in this box. Now, when we go, the next issue is what happens when we go to macro level. Say we are describing bodies like, say, this desk, and they contain a lot of molecules, a lot of atoms, etc. Does this form is this form preserved or not? And the answer is no, it is not. And on the macroscopic level, you get additional terms related to dissipation. And the next question is, does the dissipation have some special structure? And this is a very basic question, actually. I do not know whether we have time to proceed to these issues. This is the question of what is the general structure of dissipative equations. Could we write this, say, variational principles for dissipation? Now I can just express my personal view that we cannot. And all right. What could I say is, could I speak for a few minutes more?
Don't worry.
No, I worry because.
It's very interesting. I don't know for.
All right. So, now about variational principles for dissipative processes. As you may know, in thermodynamics, when we go to irreversible processes, there are quantities of two types. Say, for example, you have a gradient of temperature and heat flux, and they are related one to another. And say, if I have a heat flux, say Qi, I is the vector index, and I have a temperature gradient, say dt dxj, then in linear thermodynamics, they are assumed to be linearly related. So there are some coefficients dij which link these two quantities. And it was a discovery made by Ansager in 1934 that these coefficients are symmetric. So dij from some actually from very basic reason. And this basic reason is this very special structure of microscopic equations. So from this very special structure of microscopic equation, it follows that these coefficients must be symmetric. Now, and this, and then the next question was, all right, how to, now we would like to write nonlinear heat equations for nonlinear heat conductivity. How to do it? And the natural idea would be, if this coefficient is symmetric, so we can write this equation in the following way. We can introduce some function d, which is equal to 1/2 dij. I will denote the temperature gradient by comma t, comma I, t, comma j. And then say that the heat flux is just derivative of dissipation or dissipation potential with respect to temperature gradient, right? So this is, if we, this relation expresses this Ansager relations, which sometimes it is called the third law of thermodynamics. And And this is what is mostly welcomed by engineers. Now you may find thousands of papers based in which nonlinear versions of, say, for heat conductivity and for all other areas in which processes are dissipative are based on this potential law. The question is this nonlinear generalization of Anzager relation? So in nonlinear version, we just assume that dissipative potential is not quadratic function, but say any function we wish. Is this a matter of mathematical convenience, or this is the law of nature? So, because here we, well, 99% sure that this is law of nature for micromotion. For macromotion, is this the law of nature, or this is just our invention? Well, it reflects the way we prefer to think. Actually, when Anzager was asked this question at the very end of his life, it was in 1960s, about how to generalize his relations to nonlinear case, he said, I don't know. Of course, he saw this is elementary step, right? From symmetry of these coefficients to say, let us try this relation. But he was not believe that this is the case. And moreover, in his first paper of 1934, Anzager gave a counterexample, that this cannot be a law of nature, so to say. And maybe I have to say also that when we speak about variational principles for dissipative processes, all variational principles for dissipative processes are based on this relation. So this is some variational principles for dissipative processes is a way to formulate dissipative laws. And do they work? Variational principles for dissipative processes, is this our invention, or is this a law of nature? So this is the question. Now, and what the Anzager counterexample was that if we add if we admit that system may involve some magnetic field, then it turns out that this relation should be modified. Namely, dij, say, for the value of magnetic field B, must be equal to dji if the value of magnetic field is changed to the opposite one. So you don't have the usual symmetry, and therefore this dissipative variational principle, or variational principle for dissipative processes doesn't work. So the question is open in essence, and now I have some answer to this question, which I published a few years ago. But this is the matter of maybe a separate talk. All right, so that's all what I would like to add to what Francesca introduced in the morning. Thank you.
More people want, any other person wants to say something? Well, you don't need to be old.
Thank you.
I am included.
Yeah, all right.
Usually in Italy, if you are not scenario, you cannot talk. You need to have a serious mental problem, and you are allowed. So I talk because I know.
Yeah, maybe after first, since they've heard everybody talk, it might be appropriate to hear some criticism about speed, level, content, something which is more practical in terms of
Yes. Yeah.
so that we don't realize on a Thursday night that somebody was going way too fast in that. So
Yeah.
if somebody wants to.
So maybe we can ask compulsory questions to young people.
So if there's one topic where a burden lost or too fast.
So my personal question to you is that maybe tomorrow you repeat slowly the last Griffith condition, because I knew it in a sense, but I need to hear it again. With Sergei, we will keep discussion at distance, because another version of the calculations he has shown you equivalent results. Maybe it was too quick. Yeah. It is the school of Novosibirsk. Calculation is like Kashan. You do calculations very good. I don't know, you are from which normal école normale? Which is your high school? No, Grande École.
I studied in the U.S.
You started. So you are from the Ivy League.
From the evening,
Ivy League.
Ivy League,
Ivy League.
in the West.
Okay, so maybe we got something. But please tell us if we are too quick. Okay. Or too slow, or... Okay.
We heard something, please.
Yeah, I say maybe
Sergei is too quick. Okay, so Sergei will go slower.
So since you asked that I repeat something, may I ask Sergei then, could you redo all your computations tomorrow?
But anyway, a remark. Sergei is Euralian, and he wants to do everything in the Euler configuration, while I am Lagrangian, and I repeat the same calculations in Lagrangian formulation. So maybe this will be good for you, because you will hear 2 times the same stuff. Okay, concerning you, tomorrow, we will discuss about the fact that maybe if you have some degrees of freedom microscopic, which you don't see anymore at the macro level, you can have at the macro level an apparent loss of energy.
Sure.
Okay?
Yeah.
And if Poincaré time for energy to come back is 2 times the life of the universe, you will never see this energy back.
Yeah.
So you may have this true, but have some dissipations.
Oh, yeah,
Okay?
sure.
So this is the first observation, but we agree with it.
Yeah.
Another thing, you say, is this a true law of nature? Don't be too Platonic.
What do you mean?
I mean that we write equations.
Yes.
We don't ask ourselves if God or nature agree. We do calculations. If you forecast good things, God wants them. If you don't forecast good things with these equations, then they are not good. So, in my opinion, there are not good equations or bad equations, or in the sense, equations told by nature to us. We try.
Yeah, but we should it is nice to know when we do whether this is our attempt or whether the nature does obey to this law. And as to this boxed equation, at the moment there is no doubt existing that this is indeed the law of nature, in contrast to what we have for dissipation.
Victor, I agree with you that these are for sure good.
Okay.
Because Lagrange agreed with this. Laplace and other people. However, there is no way for knowing if your conjecture is good or not. So you try and you see what happens. I mean, if you don't deduce because you have no mathematical tools, if you are not able to deduce from this equation something, then you have to hope.
Yeah, all right.
So,
okay.
but anyway,
okay.
I think that this kind of...
Just a question about most functional you wrote. Because so you wrote variable principle for
give you
integration.
this book about ancient Greeks, because our discussions were already discussed.
Okay, all right.
This is...
Also integrated in space.
Yeah.
Also in space.
Also in space. Yes. Now the question is, in physics, particularly know how to construct models. So first of all, you consider just reversible process, use Hamilton's principle of restriction, and you consider equation data A is equal to 0. And then you propose some dissipation function, what Victor showed us, with some Zagier condition and so on, and you write equations by using this Hamilton principle 1 over 2 G over Q dot. This is just friction force. Okay? This is a way to construct mathematical models of physics. Now, my question is, okay, we have heat equation here. Is there a rational approach to say, okay, I have some dissipation system, this is a way to write functional. And this is a way to say, okay, so the Euler equations, Euler-Lagrange equations for this functional are is a heat equation in this case. Okay, so how to proceed if you have just how to construct in a rational way functionals for which the Gauss equations are Euler-Lagrange equations. Because there are many people actually in Germany especially who say, okay, we discovered a new approach for description by rational methods, all dissipated processes and so on. So what is your opinion? So my opinion, it's just artifact in the sense, just by chance. For example, but it's not a method to construct Gauss equations of physics. It is like equation, okay, with vibration, x2 dots plus x plus lambda x dot is equal to 0. This is friction. But you can write the functional a equal to q naught q1 exponential lambda t x squared over 2 minus x squared over 2 es. It can be checked that the Euler-Lagrange equation for this functional are exactly this equation. But it's just by chance. There's no physical explication of this fact, just mathematical. Are you agree with that? That it's just artifact.
Yeah.
Okay, so.
Yeah, that's right.
The road is more special functional, so it's like, it's interesting. But it's just by chance.
We are dangerously shifting towards Platonism, so let us stop here, I propose. But these discussions, in my opinion, are very useful because we need to teach to young people how to build new models. And this is the only way to discuss how incapable we are. Okay? Okay, so see you tomorrow morning.